Thank you for coming. Thank you for being here. Good morning, good evening, good afternoon, wherever you are. So today we have the last lecture in the series on the basics of level set-based structural topology optimization. The recording is streaming live on YouTube as usual and will be available there later also. So please tell your friends. And I will just quickly do a little bit of advertisement before we get started. So let me just share my screen quick. Uh, Here we go. So the details of the next webinar are not public yet. They will come. It will be sometime after the summer holidays. To keep up to date, please go to the website and you can sign up with the Google form for the newsletter. And if you don't have access to Google because of where you are located, you can also send us an email at this email here. I'm still working on getting a nice automized mailing list system that will also be rolled out during the summer is the plan. So please sign up for the newsletter to keep up to date. And super quick introduction here. So we have Professor Grégoire Allaire and senior researcher Charles Dapogny will be giving us this last lecture on the basics of level set-based topology optimization. And I think before we get started, I'll just repeat what I usually say. At the bottom of your screen, there should be a Q&A button, so a speech bubble with a question mark and Q&A. So if you have any questions during the lecture, you can write them in during the lecture. If you have questions at the end, you can write them in there also, and we will answer them either during or at the end. And with that, I think, Charles, you are starting, so you can go
I
ahead.
can share my screen. So hello, everyone, and welcome to this third webinar of the series. So this webinar is devoted to one particular, let's say, improvement of the level set methods, which still allows for arbitrary deformation of the shape between iterations, but also enjoys an exact mesh of the shape throughout the iterations. So the webinar is divided into three parts. At first, we're going to view a few basic concepts about meshing and especially remeshing. Then we shall present the benefited level set methods, including remeshing, in a second time. And then we will deal with applications, for instance, in multiphysics, or in optimization of shapes so that they withstand fracture, or in optimization of boundary conditions, for instance. All right, so before getting started, let me remind you about the classical level set method. We have seen that it's one principled way to describe arbitrary deformations of an optimized shape. The rationale is that we are given a fixed mesh of the computational domain, and the shape is defined via a level set function, function phi, such that the shape is the negative subdomain, the negative subregion of this level set function. So the mesh is fixed, and the level set function is defined typically at the vertices of the mesh and is updated as such. So one drawback of these methods that we have mentioned is that mechanical computations, typically the solution of the linear elasticity system, if we are in structural optimization, it cannot be done exactly on the mesh of the shape because the shape is not meshed. So we have to use some kind of fictitious domain methods to approximate this state equation and the agent equation by an equation which is posed on the total computational domain, which is meshed. Typically, when we are in structural optimization, we approximate the linear elasticity system by the assessed material approximation. So we fill the void here of the shape inside the computational box by some very soft material. And so the elastic displacement of the shape, which is displayed here, is very close to that predicted by this approximation. So there is a principled way to do this approximation in elastic system and in other contexts, but it's much more difficult to come up with some accurate such fictitious domain methods in more difficult physical contexts, typically multiphysics optimization, where the boundary of the shape bears complex physical effects. So here we are going to present a variant of the level set methods, which still enjoys an arbitrary shape evolution, which is guaranteed, which is rooted in the level set methods, but also enjoys arbitrary, accurate, and non-intrusive computations of an exact mesh of the shape at each iteration. So we're going to combine two shape descriptions, the level set representation that we have seen so far, and also a body-fitted mesh representation. The mesh of the shape, which is in yellow here, will be in some sense a sub-mesh of a total mesh of the computational domain. And we describe two operations, meshing algorithm, especially, to go back and forth between these two representations. So let me start with a few concepts and a few definitions about meshing and remeshing. So we consider a domain omega in R2 or in R3, and a mesh, a simplicial mesh. It's a mesh, it's a decomposition of omega in triangles when we're in 2D, or in tetrahedra when we are in 3D, like in these two examples here. Most often, we require several things of this mesh. We require first that the mesh be valid. That is, no two different elements intersect like this. This is typically an invalid mesh. We also require that the mesh is conforming, meaning that if we look at two elements, then either they share nothing, or they share a vertex, or they share an edge, but they don't. It is not possible that we have an hanging edge like that falls in the middle of an edge, which is over here. And so this is typically a non-conforming mesh, and this is a valid and conforming mesh like we like. Okay, still going on with definitions about meshes. The mesh naturally comprises a surface part, which is very important for applications, meaning that the mesh accounts for a domain, and the surface part is the collection of segments in 2D, or the collection of triangles in 3D that make the boundary of the domain defined by the mesh. So typically here we see that the boundary of the mesh will be this line here, the collection of these segments, external segments that are here. So here we have a representation of the boundary mesh associated to a 3D mesh in yellow. So in practice, the mesh domain is not a polyhedron. The shape is not a polyhedron. It's just approximated by a polyhedron, which is the mesh itself. So the surface part of the mesh is meant to be an approximation of the boundary of the shape. So now let's come to an application to a notion which is very important when it comes to meshing, to the use of meshing. It's the notion of quality of the mesh. So I'm pretty sure that you have already come up with this notion, and we are going to actually distinguish two different notions that are complementary for defining the quality of the mesh. The first one is probably the one that is the most well-known, the best known to the people practicing finite element methods. It's related to the shape, in some sense, of the triangles. So, for instance, it is known that the quality of a finite element simulation is often linked to how much its elements, its triangles into the tetrahedra in 3D, are close to being regular. We know that when we have very, very flat elements, for instance, the quality of the numerical resolution is typically pretty bad. So we are going to measure the quality of the mesh by the quality of its triangles. And the quality of the triangle is just an indicator that takes into account that it's, in some sense, the vertices of a triangle or a tetrahedra, and returns something which is close to 0 when the triangle or the tetrahedra is nearly flat, and close to 1 when it's close to being regular. And typically, we ask that this quality factor smoothly discriminates elements that are very bad, not too bad, okay, pretty good, and very good. So we have a whole range of taxonomy for distinguishing elements. And typically, a quality factor is something like that. So it's a volume divided by some kind of weighted sum of the length of the edge. And you see that it's something that goes to 0 when the volume goes to 0, but the length of the edge don't go to 0. Typically something like that, which is going to give you a needle. So there are a lot of ways to calculate quality of elements in a mesh, and this is one among the all possible. Another very important notion, which is complementary, is the notion of geometric quality of the mesh. So recall that the surface part of the mesh, that I called ST, is only meant to be an approximation of the boundary of the shape. And what we want is typically that this approximation be good, meaning that the discrete parts, the discrete border ST, be close, in some sense, to the continuous border d omega, meaning that the Hausdorff distance between the two be less by some tolerance that I call epsilon. So let me remind you that the Hausdorff distance between two compact sets is a maximum between the distance from any point of K1 to K2 and the maximum distance between a point of K1 of K2 to K1. So whatever the definitions, the Hausdorff distance is low when the difference between the continuous and the discrete approximation is small. So typically, this is an illustration of the difference between the two notions of quality that we have outlined so far. This is a mesh of a shape which is of good finite element quality. You see that the triangles are pretty close from the irregular, but it is a bad geometric quality because the discrete part, the discrete mesh, the discrete surface mesh is far from the continuous domain that we imagine underlying behind this mesh. And this is a good finite element quality mesh and a good geometric approximation of the domain that we intend. All right. So now let's make a distinction between meshing and remeshing. So what is meshing? Meshing starts typically from the datum of a mesh of the boundary of a domain, so just with triangles, and we aim to fill the volume inside with tetrahedra that are supported and whose boundary part is exactly the initial surface measure we have given. Typically, we start with something which is empty like that, just surface triangles, and we aim to fill the volume with tetrahedra. So this is a very difficult operation that is not always, even with the best meshing softwares, it is not always guaranteed to succeed. Remeshing, on the contrary, it starts from the datum of an initial valid conforming mesh of omega. But the mesh may be pretty bad because it may be pretty bad with respect to its finite element quality, or it may be pretty bad with respect to its geometric quality, or both. And typically, we aim to modify this mesh into another mesh of the same shape, which is of good finite element quality and of good geometric approximation quality. So typically, how do we proceed with remeshing? We start from this very bad mesh here, and we apply 4 remeshing operators that we intertwine in several ways. So there is a whole cooking recipe, in some sense, to intertwine, to use, to apply these operators. So typically, one of these operators is a splitting of edges. When we have edges that are too long, we just split the edges and reconnect the elements so as to have smaller triangles. We have triangle or tetrahedron collapses. So when we have a very, very small edge like that, we try to merge its endpoints so as to remove the 2 needles, the 2 very thin elements which are here. And this gives the resulting configuration which is here. Yet another operation is the swapping operator. Typically, when we have an edge which is like that, we can try to suppress this edge and to retriangulate the cavity that is left by removing this edge and the tetrahedral that, typically by triangulating the polyhedron which is given by the remaining vertices here, and trying to reconnect in the best possible way. So this is a very combinatorial operation, but this is an operation which is crucial to try and improve the quality of the mesh. And the last operation is a relocation of a node. We can try, without changing the connectivities of the mesh, to move slightly the point to try to improve the quality of the overall configuration. So by intertwining these 4 remeshing operators, we can try and gradually improve a lot of application of these operators to improve gradually the quality of the mesh. So often, this improvement of quality of mesh is also complemented with some other feature, which is very cheap to people doing finite element a posteriori estimates. Often, the user wants the mesh to achieve a particular size on a particular part of the mesh. Typically, for instance, the user is free to give an indicator to say that in this part, in this region of the mesh, I want this size of elements. And typically, this size prescriptor may come from finite element estimators, for instance, if you have some, or geometric requirements. And typically, the user can supply a size map, typically a map that gives a value at each vertex, saying that near this vertex, I want this particular size for the edge near this element. Typically, if we start with this mesh here and the user gives this size map, which is very, very small in the blue part, which is here, after remeshing, this gives something like that, still a valid conforming mesh with very, very thin elements, very refined elements here, according to the user prescription. So this size prescription can also be made anisotropic, meaning that at a particular point, we want the mesh to be very thin, to have very small size in particular directions. So there is a way to encode this information in a Riemannian metric, but I'm going to skip this part because it's not needed in the following. And just, will content myself giving an example. Here is some the simulation of a supersonic flow using an adapted mesh in an isotropic way, when you see that the mesh elements are very elongated in particular directions that were supplied by the user. So we can really encode during remeshing size and orientation information for the elements. Well, let me finish with this very brief tour of meshing and remeshing with a word of advertising. That all the features that I have discussed so far, they are implemented in an open source library, which is called MMG. And so it comes with a series of tutorials to make it work. And all the simulations that we are going to show today use this remeshing library for our purpose. So feel free to go and download it and use it for your purpose if you are interested. So let me now focus on one particular operation involving remeshing, that is the heart of the methods of the body-fitted level set method that we will present just afterwards. It's called isosurface discretization. So the idea is like this. We start from the datum of a hold-all domain, a fixed computational domain, which is endowed with a simplicial mesh T, typically this guy here. And we give ourselves a level set function phi defined at the vertices of the mesh T. So here is a color map which shows the values of the level set function phi at the vertices of this mesh. And now we wish to construct a new mesh of this computational domain in which the zero level set of phi appears explicitly in the mesh, meaning that a collection of the triangles of the mesh of this omega will appear explicitly as triangles in the mesh here after modification. So there is a simple way to do that with the ingredients that I have presented so far. It's a two-step solution. So we start with this datum, the datum of a mesh of the computational domain, at the vertices of which there is our level set function. And we first split explicitly the zero level set of this function phi into the mesh. So here we have our initial configuration. So you can see that the zero level set of the function phi is not discretized in the mesh. We can identify where it passes by just looking at the values of the level set function at the vertices of the mesh. And then in the second time, we just split them explicitly by just adding the points where the zero level set passes and reconnecting accordingly. Okay, so this is a very simple thing to do. But of course, if we do that, it is pretty bad because we create very, very bad elements. Oops. We create elements that are very, very small here, as you have seen. But then we have a valid mesh in which the domain omega is explicitly discretized, a valid and conforming mesh, and we can apply remeshing, quality improvement, quality-oriented remeshing to improve the configuration and then get a new shape, a new mesh of the computational domain in which the shape omega is explicitly discretized as a good quality mesh. So here is an example in 3D now. So we have a cube here, which is equipped with a tetrahedral mesh, and at the vertices of this cube, there is a level set function that exists, and here are some isosurfaces of this level set function. So first, we split explicitly the zero level set, zero is the surface, into the mesh. So here you only see the surface part, but you have to imagine that there are tetrahedra outside and inside the elephant. And of course, like you see on the zooms, you have a mesh which is of very, very bad finite element quality. It is valid and conforming, but of very bad element quality with very, very flat elements. And then we apply this quality-oriented remeshing to obtain a new high-quality mesh of the resulting configuration. So here we have a mesh of the total computational domain with a mesh inside. A sub-mesh is a mesh of the shape. So if we just so you have to imagine again that you have tetrahedra outside and inside the shape which is here. And so, Grégoire, I will let you present the method itself.
So let me introduce now, knowing these tools from remeshing, the general strategy for this body-fitted variant of the level set method. Okay, so again, we minimize some objective function depending on the shape omega with some equality constraint. If you want to have inequality constraints, that's the same. Of course, the objective function of some of these constraints are computed by the solution of a physical model that we call U index omega. Good. So the key idea is that at each iteration in a fixed Haldane domain D, which has a simplicial mesh, we have an iteration of the shape omega n, which is described by two different ingredients. First, it is described by its mesh, an internal mesh, that's the yellow mesh on the left, but there is also a level set function phi n, which is defined on the complete mesh of the box capital T. And then, as Charles explained to you, we have two ingredients to go from one representation to the other. Either to compute the level set function from a domain, we compute the sign distance function, and then a classical algorithm is a fast marching method. I'm not going to discuss it, that's very classical. And then to go from a level set to a mesh, there is this idea of the isosurface discretization, which was just introduced to you by Charles. All right, so when, at each iteration of the optimization algorithm, you need to compute the solution of the state equation and possibly of some adjoint equation, and you do that with the mesh of your domain omega that is on the yellow part. You completely forget the green part, you only compute on the yellow part, and so that's the gray mesh in the middle picture here. And that's what you give to the finite element solver. You forget about the exterior part that you don't need for the finite element solution. And then the second step is, once you have computed the state and the adjoint, you have a shape derivative, and then with this shape derivative, you advect the level set function. And to advect the level set function, you are going to solve this Hamilton-Jacobi equation, and you do it on the complete mesh. So not only on the yellow, but also on the green mesh, okay? So while in the first finite element computation, you just use the internal mesh, the yellow one, in the second step, where you move the level set function, you use the two meshes, you compute the advection on the two meshes. Good, so let's look, for example, at this classical cantilever problem, which is clamped on the left, and on the right you have a vertical load. You see the solid part in yellow and the green part representing the holes, but this is a complete mesh. And then you have the corresponding sign distance function, the level set on the right. Okay, so when you compute the finite element solution, you forget about the green part, you only have the yellow part, and you solve your finite element. And for example, here you can look at what we got as the solution, combination. If we minimize compliance, that the energy density, which is going to be the integrand of the shape derivative. So this is plotted on the right. And then in the next step, you move your level set function on the wool mesh. And so you see typically on this picture here that the yellow part now has a boundary which is red, and this boundary which is red is not exactly corresponding to the boundary of the mesh. Okay, so you have moved your level set function to new positions which are not in the mesh, either yellow or green. And so the next point is that we need to remesh so that this red curve now is included inside the mesh. And so that's the first step in this remeshing. We simply cut each triangle and we produce new triangles that fit the zero level set function. But of course, the quality of the mesh is very bad. As you can see, you have very flat elements, as you can see in the zoom part. So the second step of the second ingredient of the remeshing is to adapt the mesh, to remesh by improving the quality, and you see the result. Now you have much nicer triangles here. Okay, so now you repeat this until convergence. And so, for example, you have on the top left first iteration, second iteration, third and fourth, and you see that you can combine a perfect body-fitted meshing with the topology changes, which is a typical feature of the level set function. Of course, if you were simply moving the mesh, you would never change the topology, but the level set function, when it evolves, can change the topology. So here is a small movie for this cantilever problem, and you can see a lot of small oscillation at the end, which is typical of convergence. small displacement until the velocity field is really zero. All right, so what are the most important features of this? The fact that you have an exact mesh means that, of course, you don't need an ersatz material in linear elasticity, or if you are doing multiphysics and if you are very important interface condition at the interface between the different physical subdomain, you are not doing any approximation. So you have a much accurate description of your physics. Another ingredient which is nice, another feature which is nice to mention is that, of course, in the submesh, you have much less elements than in the full box. So actually, if you only have one physical domain, you have a much cheaper computation because you have less element in your submesh than in the complete mesh. Another feature, another interesting advantage is that you can call any mechanical solver because now you have a perfect mesh of your domain. There is no gray area, no intermediate densities and so on. So you can call any finite element software that you like in a black box fashion. Okay, and of course, with this perfect meshing, you have a very accurate modeling of geometric quantities like curvature, thicknesses if you have thickness constraint, and so on and so forth. Of course, you can still have a very large motion of the and topology changes because of the level set method. And finally, of course, there is some computational overhead because of remeshing. But remember, remeshing is cheaper than meshing. And then this overhead can be partially compensated. We will have some figures to show you on some example. This computational overhead can be compensated by the fact that you have fewer elements in your finite element computation. So let me show you a few benchmark examples. Again, a compliance minimization for this 2D crane with a volume constraint, so something very classical again, but you have a perfect mesh. To tell you the truth, for compliance minimization, it's not really a mandatory method. But if you go to some more complex physics, then a perfect meshing would be nice. Here we can see one advantage of this method. Remark that at the beginning, because of the initialization, we were having some holes, and then along the iteration, those holes are closed. And why they are closed? Because actually you cannot see it, so you have two views, but there will be a very thin shell that replaces these mixtures of bars and holes. And actually in 3D, very often thin shells are much better than a combination of bars and holes. But you cannot see it if you have a rough mesh. And here, because you remesh, you can do this meshing of this kind of thin shell. So that's the first advantage of this method here. Here, this is another example on a much more complicated physics. This is a model where a model of crack propagation. So we have a load which is here vertical and which is increasing over time. So it's a quasi-static evolution. And we have a model that is a so-called phase field model of Frankfurt and Marigot to compute crack propagation. We minimize the negative total energy, which is here, which is a measure of how which is, if you minimize it, you want less crack propagation to appear because this guy will be very very positive, sorry, if you do crack propagation, of course, with the volume constraint, and that's our initialization. And here you see what is a solution for just compliance minimization, standard compliance minimization. And here, this is a solution for this model of crack propagation, right? And you see what is the crack in this phase field model for the initialization. The fact that for the structure optimized for compliance, you still have a crack. But of course, for the structure which was optimized with this complete phase field model of crack propagation, you don't have any more crack. And of course, that's a better design for minimizing the crack propagation. Finally, another example, which is a first insight into multiphysics, it's a heat conduction problem. And so actually what we optimize is not the shape, but this is the interface between two conductors, high conductors gamma 1 and the low conductors gamma 0. So the high conductor is attached to a Dirichlet part where the heat can escape. And then you have so on gamma D, you have a zero temperature. All the other boundary of this box, this cubic box D, are insulated, so Neumann boundary condition. And then we have a constant source term. And so the idea is if we want to minimize the average temperature, that means that we want to have the design of the best conductor so that we extract it to this lower plate gamma D as much as efficient as possible. So that's the initial, it's kind of a cube of the good conductor. And you see the propagation of the interface during the optimization. It's creating very thin plates or shells on some elongated rods, okay, which are collecting heat everywhere in the volume and carrying it to the bottom plate where heat can escape. And of course, this can be done because of remeshing. With a fixed mesh, you will not see any detail smaller than the size of your fixed mesh. If you are interested in this, another word of advertisement, this is a fully open source implementation with Python mostly, which was done by Charles and our joint former PhD student Florian Fépon, and you have a paper in the compte rendu of the Académie des Sciences de Paris that explain everything on those examples. Okay, maybe if we still have time, I will just discuss the first example, which is the optimization of the internal structure of an electrical motor. So here are some pictures of an electrical motor, and we are looking here only for the moment on the magnetostatic computation of a 2D section of this electrical motor. All right, so you have a stator, which is at the exterior with some coiling, which are represented here, which is not optimized. And then you have the rotor with an air gap between the rotor and the stator. And so what we optimize is exactly the rotor, which is made of two material, a ferromagnetic material and air. But both material appear in the computation of the PD because, the electrical field and the magnetic field do not stop at the boundary of the ferromagnetic material, but they also occupy the air. So the computation is done on the union of the rotor and the stator. All right. The equation in this 2D context is an equation for the vector potential, for the scalar component of the vector potential of the magnetic field. It's a nonlinear PDE equation, and actually there is a saturation effect in the ferromagnetic material, which means for high gradient of U, large values of the magnetic field, nu will increase. And then we want to maximize the mechanical torque, so we want to have the best behavior under a given coil, current applied to the coil in the stator. So here is a picture, only the interior rotor is optimized at the initial configuration. You have a zoom here, and you can see the evolution of the geometry. No topology change in this simple setting. What is very important is that the size, the optimal size of those small ligaments here is linked to the saturation effect of the PDE, of the magnetostatic equation. And this cannot be predicted in advance before doing the computation. So having an evolving mesh is something interesting. So I leave the floor to Charles for the other example.
Thank you, Grégoire. So yes, so let me turn to other type of examples. So as I mentioned at the beginning, this type of body-fitted level set method is typically very interesting for multiphysics applications where there are complex effects at the boundary between the different phases at play. So let's consider typical multiphysics applications mixing structure, fluid, and temperature effects. So we consider devices which are typically enclosed in a fixed computational box D, where there is a solid phase, which is called omega or omega S, and its physics is characterized by its elastic displacement. There is also a fluid phase called omega, which is complementary to the solid phase, which is characterized by its velocity d omega and its pressure p omega. And typically, this one is characterized as a solution to the Navier-Stokes equations. And there is also the temperature variable, which depends on convection effects within the fluid and diffusion through the solid parts, and this, which lives on the total domain, fluid plus solid. So typically, this type of formalism allows to model water turbines or heat exchangers. So let's consider a first example, which is the optimization of a solid obstacle in a fluid structure interaction context. So we have solid obstacle omega s, which is here, which is included in a pipe, which is crossed by a fluid. So the total domain is this box, which is here, which is called capital D. Omega s is a subdomain of capital D, and the complementary domain is the fluid phase omega f. So the physics at play is the following. There is a fluid as fixed as a node incoming profile, and the Navier-Stokes equations are solved inside the fluid parts to characterize the velocity and the pressure within the fluid. So the fluid is pushing on the structure, which exerts a stress on the structure, and this calls for a very non-trivial boundary condition for the solid parts, which is a solution to the elastic display, to the linear elasticity equations, with this complicated stress boundary condition at the boundary. And in this context, we aim to optimize the shape of the solid obstacle with respect to its solid compliance. We want to maximize its robustness under some volume constraints. So here is how it goes. So here you see the optimal, the initial shape of the obstacle, which is very dumb initial design. And here you have some isovalues of the fluid intensity of the fluid of the fluid velocity. And so here is what we obtain in the course of the practice of the level set body fitted methods. And so here you have to imagine that you have elements that are everywhere inside the solid and outside the solid to calculate for the fluids. But the boundary conditions between the two are exactly calculated at the interface when solving for the solid problem. So this is one example where it would be very difficult to find out some equivalent, in some sense, fictitious domain methods to account for the boundary of the fluid, the effects at the boundary of the fluid, if the latter were not completely explicitly discretized in the computational mesh. Another example in this setting is related to the design of heat exchangers. So now we consider still a fixed computational box here with two phases, solid and fluid, but the fluid domain is itself divided into two parts. There are two pipes. One is omega F hot, it's crossed by a hot fluid, and the other one, omega F cold, is crossed by a cold fluid. And so in both pipes, the Navier-Stokes equations are governing the physics, and in the solid parts, we neglect the deformation of the solids, but we consider the diffusion of temperature through the solid parts. And so in this context, we want to optimize the shapes of the two pipes so that the heat exchange from the hot pipe to the cold pipe be maximized. Of course, if we do that, we have to impose some engineering constraints, and typically the fact that the two pipes must be separated by a minimum distance, as to maximize the fluid transfer, the two pipes will be stuck to one another, which is not possible for manufacturing reasons. And we also impose a volume and a pressure drop constraints of both pipes. So here is the initial design. So it's a very dumb, in some sense, network of hot and cold pipes, which is a bit difficult to interpret, admittedly. And here is what we obtain by applying our methods. So still we see a lot of topological changes. Thin shells again, like those that Grégoire pointed out, but also some holes that are some kind of toruses that emerge through these thin shells when they are, as long as they change topology. So here the computation is pretty enormous, and the mesh is something like 2 or 3 million elements, I don't remember exactly, and the computation takes something like 8 days on multiprocessor computer. Okay, so let me now speak to another setting that is possible with this body-fitted level set method, which is the possibility to optimize the shape of regions bearing boundary conditions of a physical problem. So all that we have discussed so far can be adapted to a different setting, that where we optimize not a subdomain of a fixed computational domain, but a subregion of the boundary of a shape. So typically here we consider optimal design problems of this form. We minimize some function which depends on a region J of the boundary of a shape. And typically J accounts for a region where we apply particular boundary conditions of a physical problem. So all that we have presented so far applies exactly to this type of problems also. And we can look at examples of this kind. So let me look at the first example in a very simple, in some sense, physical context, which is that of the optimization of microosmotic mixers. So microosmotic mixers, that's very, very small devices that are used in microfluidics. And so you have to imagine that two fluids come from the input channel, which are here, and go out from the output channel, which are here. And the goal of the microosmotic mixer is to mix these two fluids. And people report that, physicists report that the mixture is all the more efficient as we apply a strong electric current at the boundary of the electroosmotic mixer. So to achieve this, we put an anode and a cathode on the boundary of the electroosmotic mixer. And so the potential that is generated by this anode and cathode is a solution to this equation here. So we see that there is a Dirichlet boundary condition, or U in, on the anode, and a Dirichlet boundary condition which is 0 on the cathode. And the rest of the boundary is insulated from the outside. So here, our design variable is the placement of this anode and cathode boundary conditions. The shape is fixed, but we optimize the shape of these regions bearing boundary conditions. So we optimize a function which depends on gamma A and gamma C. With respect to this thing, we want to maximize the electric power inside the domain omega, which is fixed, with respect to the shapes of these two regions. So we start with something which is empty. We have no cathode and no anode. We first use a mix of topological derivatives that we presented in the second webinar to initialize, in some sense, the anode and cathode patterns. And then we go on with the boundary variation methods coupled with this body-fitted remeshing method that we just presented. And here is what we obtain. We obtain the design of the anode part on the left panel and the design of the cathode part on the right panel, which is here. So you see again very, very, very thin features that emerge in the course of the resolution. And so let me terminate with one last example in this setting of optimization of boundary conditions, which arises in the field of acoustics. So here we consider an obstacle, omega, which is here, which is placed in the whole ambient space. And so we send an input wave, an incoming wave U in on this obstacle. And as a result, depending on the shape of this obstacle, there is a scattered wave U omega. And typically, this scattered wave can be used to detect or reconstruct omega, which is good in some applications, typically in medical imaging, where it's a principle of tomography. But it's very bad for military applications, for instance, when you have to imagine that omega, it's a stealth object, typically a submarine, and you want to kill, in some sense, the reconstructibility, the identifiability of omega from the shape of from the structure of the scattered wave. So here we aim to optimize the repartition of two materials on the boundary of the obstacle. One is sun-soft, meaning that there is some kind of absorption of the incoming wave. The other one is the sun-hard material, meaning that the wave bounces on the boundary of this, on this part of the boundary, in some sense to cloak omega, meaning to minimize the intensity of the scattered wave. So of course, we will do that with a constraint on the volume of sun-soft material because the absorbing material is expensive in practice. So the setting is like this. Omega is an aircraft, which is meshed here, and which is included in a large mesh of a whole computational domain here. The incoming wave is given by this. And typically, the boundary of the, so the obstacle here is fixed, but its boundary is decomposed into two regions. One bears Neumann conditions, the sun-hard conditions, and the other one bears Robin conditions, the sun-soft conditions. And the scattered wave is a solution to the Helmholtz equation, which is here, which depends on the repartition of sun-soft and sun-hard materials at the boundary. And we want to minimize the amplitude of the scattered wave on the constraint of the surface area of the sun-soft material. So we start with something which is nothing, just sun-hard material only. And here is what we obtain. So here again, you have to imagine that we have a whole mesh, a whole 3D mesh of the computational domain. But here I only represented the mesh of the boundary of the obstacle, where the gamma n and gamma r are optimized. So one word to conclude about the assets and drawbacks of this method that Grégoire has already partly mentioned. So the assets of this method is that an exact mesh of the shape is always available at each stage of the optimization process. So this is handy and full, for instance, for geometrical computations, but it also means that the mechanical computations of the workflow, they can be realized without any approximation, without asset material, and in a very accurate fashion, and also in a non-intrusive fashion. You can send the pack of tetrahedra of the shape to your favorite finite element solver, So I personally use FreeFem, but some other people, for instance, I know use Phoenix or GetFem, but you could use whatever you want, commercial solver if you want. Some drawbacks are about this method are certainly that some of its operations, and not only those devoted to remeshing, are a bit delicate to handle. But hopefully, there are some open source libraries. So I have made advertising for the one that we are with Grégoire and other colleagues developing. But maybe there are other ones that will do the job. And the method occurs computational overhead, of course, that is quite moderate for the reason that Grégoire has mentioned. So one final word about what we want to go, where we want to go from this, still using these body-fitted remeshing methods. So we wish to treat very complex multi-material patterns, such as in electric motors, for instance. So the example that Grégoire has presented about electric motors is one of a series where there are much more complicated ones with several phases, for instance. We want to go to parallel remeshing to deal with very large-scale applications where it makes sense also to parallelize the remeshing process. So we have started to develop a library, par-MMG, a parallel version of the MMG library. And we also want to develop this body-fitted level set method for the optimization of open surfaces, typically surfaces that whose also the boundary is to optimize, typically in shells, in refractive or reflective surfaces in optics, or for electromagnetic screens. And so with that, thank you again for attending this webinar, these free webinars. And Grégoire and I will take any questions if you have.
Thank you so much. Thank you very much. So just a reminder, if you have any questions, at the bottom of your screen, there should be a button with a speech bubble with a question mark and Q&A underneath. Click on that and you can write your questions. While we're waiting for some questions to come in, I have a few questions. So these are in some sense, you're doing some discrete updates of the shape. Does this lead, or it's a multiple part question. So I think it leads to some oscillations, right? So you can see on some of your optimizations, the surface is a little bit nervous. Like,
Yes.
how big of an issue is that? How have you experienced it? I think especially for your surface physics, or for instance, on slide 56, there was quite a lot of these oscillations. But how do you have some
Maybe,
general comments on that?
yeah, I have. Okay, I will discuss first of the volumic case,
Mhm.
not of the surface case. The key point is that we are using continuous gradient, and then we use them for a discretized model. And then it's well known that optimization and discretization do not commute. And so even with the standard level assessment method, there will be always some slight oscillation in the sense that the shape derivative is never exactly zero.
Mm.
Okay. And this is even worse if you change the mesh, because now we change the mesh because we remesh. And so that means that not only you have an approximation between the continuous gradient and the discrete gradient, but the number of degrees of freedom is not the same. So that's why we have those oscillation. And then maybe another effect is that, of course, in remeshing, there is some kind of smoothing parameter saying that we don't want to have too many small details. And so maybe your gradient is trying to produce small details and your remeshing is saying, well, let's keep it above a certain size. So that's one more source of oscillation. Now, maybe
Okay.
Charles has something to add.
That's exactly what you mentioned. There is also just to complement your answer, Grégoire. For exactly the reason that you described, we usually add a small tolerance about to just not to impose that strictly the cost function will decreases at each iteration. We allow it to slightly increase for a few iterations so that it doesn't get stuck to a local minimum, for instance. That's one reason. Typically at the end, so we could do something much more clever than that. Typically say that after 200 iterations, then if it doesn't want to decrease anymore, then it could be declared to converge. So we could certainly do that, and we did not that.
Okay. Okay, so we have some questions from the audience here. So one person asks, do you have any opinions on curved meshes And why do you think it's not very popular?
I would say that it's not popular because it's very difficult. Uh, no, I mean, so just so it's just to give an idea. So I have not, I have, we have presented in a very few slides the remeshing part of this framework, but the remeshing part is actually quite intensive in terms of programming effort. So the library MMG, for instance, it's written in C, and it's something like 200,000 lines. So it's a big code. And there is not a lot of theory about that. It's a lot of cooking, meaning you tried a lot of strategies for remeshing. And this is just for flat tetrahedra. The good thing in flat tetrahedras, every time you do an operation, you have to verify in your machine that you do not make the mesh invalid. For instance, I have not talked about that because it's a bit of kind of the meshing folklore. But typically, if you look at this particular operation, the collapse operation that I have presented, oops, here, for instance, if you do not check the result of the collapse, for instance, you can make invalid mesh. Typically, this point can go to this point, and this element could overlap this one. So every time you apply an operation like that, you can detect that you are making elements invalid by calculating Jacobians of the mapping. And then you have to simulate the process, say, okay, I'm making something invalid, so I'm not doing this operation. Then I do operations in other parts of the mesh, and maybe in the flow of making some improvements, in the end, the motion will become possible. And these detections of making the mesh invalid, they are very cheap to compute with flat meshes because the Jacobian of the transformation is one determinant computation per element. But with curl mesh, it's nothing like that. It's much more difficult, and it's very difficult and very costly to detect that you are not creating an invalid mesh, for instance. So this is one reason, but there are many reasons that make that handling. It's not that it's not very popular. I think people dream in the industry to use curved mesh, but it's already very complicated with flat meshes, for what I know. And so curved meshes, typically in this moving setting, well, I would be very frightened to try to do that.
Okay, thank you. We have a question that aligns with one of my other questions. So, how do you enforce length scales? So, for instance, on slide 53, you impose this distance between the two fluids in the heat exchanger. How do you do that in practice for this method?
For this heat exchanger example, this was very easy because actually we have two different level sets, one for the hot fluid and one for the cold fluid, because you don't want them to cross. So there are two different ones. And then computing the distance is simply by the sign distance function. And then you compute an LP penalization because, of course, that's a maximum constraint, but you regularize it as an LP constraint. And so that's very easy. And then to compute shape derivative. So this one is easy. Now, if you had only one level set function, meaning only one fluid, for example, and you don't want to have two small details, then there are notion of minimal or maximal thickness. It's a bit more tricky, but it was done in the context of level set function by my former PhD student, Georgios Michailidis. And so it's completely doable. That's purely geometry constraint, which are easy to calculate in the level set setting. So no filter, no nothing. You just compute sign distance function.
Yeah, you can model these constraints by functions that depend on the shape via the sign distance function.
Yeah.
You can calculate shape derivatives with respect to that, and there are strategies to impose that.
So does that require that your level set is a sign distance function, or do you reconstruct a sign distance function?
You reconstruct because
Okay.
maybe maybe you have the minimal thickness only at some part of your domain and not at the other ones. So you always reconstruct, but it's not very expensive.
And in these body fitted methods, you always, when you regenerate the sign distance function, so you regenerate a level set function at each iteration, like Grégoire presented here, for instance, every time you have to choose one level set function to generate. So you choose the sign distance function because it's very cheap to compute with the fast matching methods. So in this setting of body fitted method, you always have the sign distance function at hand.
Okay. Thank you. There is an equation about AI, so let's get it over with. Everybody wants to know. Uh, could you integrate these methods with AI or machine learning for faster optimization?
Ah, Grégoire.
Good point. I have a PhD student who is working on this, and so our strategy is not to replace everything, but to try to either improve the optimization algorithm. So we have an optimization algorithm. Maybe one possibility is you remember this Hilbertian regularization, which uses Hilbert scalar product to improve the smoothness of the shape derivative. Why not choosing another scalar product? And so we could learn the best scalar product. So that's a direction of research. Or another possibility would be to say, well, can we not learn how level set function evolve and have a representation by a neural network of level set evolution, and then we will optimize level sets that will be parameterized by neural networks that will, favorize in some sense the good topology changes. But the idea is not to replace
Mm,
all the machinery because
Mm.
I believe it's not reasonable at the moment.
yeah,
But there will be other possibilities, maybe. I don't know.
yeah, yeah. It's hard to predict the future, right?
Yes.
So the last question from the audience is, do you have any advice on the speed at which you should advect the level set? So they write, in our framework, we do not use the dash no CFL option of the
Mhm,
library
mhm.
advect to keep a
Okay.
clean interface, but it is very slow.
Yeah. So yeah, actually you choose. So this is related, if I understand well the question, to the choice of the descent step, right? So typically, what we do, one way to do that, I don't know if it's the standard way, the canonical way to do that, but it would be, for instance, to, let's say, normalize the descent direction so that it has maximum amplitude 1, and then to take a time step which is based on the mesh size. So typically to say that at one iteration, we do not advance more than, let's say, 2 or 3 mesh size, just to have some kind of sensible way to size the time step. So this is one possibility to do that, so that you do not have like dramatic changes that precipitates the optimization in a bad local minimum just for the sake of an initial gradient, which is very disconnected to what is relevant for the shapes afterwards.
My experience is that somehow it depends on the problem. For a simple compliance
Mm.
minimization problem, if you advance the level set function a lot, meaning maybe you choose time steps such that you will cross 10 cells at each iteration, that will work. Now, for a
Mm,
much more delicate problem, you should not go too fast because once you have broken, let's say, on this picture that we see, we have some bars, and once you have broken the bar, it will never come back.
mm,
So if you go too fast at the beginning, sometimes okay, you go fast at the beginning, but maybe you fall down in a local minima.
mm,
That's a problem of all those methods, and especially the level set method, where you may be more sensitive to local minima. So sometimes you should not go too fast.
Mhm.
But then for easy problem, if you go fast, that's okay. In any case, the CFL condition should not be the descent
Mhm.
step. You
Yes,
should update the descent step independently of the CFL condition.
yes, yes.
okay. Yeah, thank you. So I have it's perhaps a bit big question, but I think it's valid. So I think this method has a lot of strengths, right? You get this exact mesh, and especially for multiphysics problems, that's a huge benefit. Um, but what is the biggest obstacle for everyone to use this? I put it on a knife set. Why are we not all doing this yet?
So, by the way, there is another question saying sensitivity with respect to initial condition.
Ah,
So,
yes.
one way of answering your question on this one is to say in 2D, we are very sensitive to the initial condition. In 3D, much less, but still, I must recognize that, you really evolve a geometry, so you're not taking shortcuts like with the density method. Okay, so that's clear that the density method, any kind of density method, can take shortcuts, but then the difficulty will be for multiphysics application. What are the mixing rules and things like this? Now, why not everybody is doing this is that it's not easy to implement MMG in a finite element software. So because first it's only using simplicial mesh. If you are using meshes where you may have other kind of geometries of cells, maybe you have some difficulty. Then it works perfectly if we have one level set or two level set, but that stays separated. Now imagine that we have a three-phase problem, but with a triple point. Okay, that was typically the topic of one of my PhD student, Thomas Gauthier, who was doing the example on the electrical motor. He has to struggle a lot to actually, a triple point is not a problem. It's when the two level set function at some point coincide, on a portion of a boundary. So you squeeze one of the phase between the two other ones, then you have to struggle a little bit. So multi-phase remeshing is still under progress.
Okay. But maybe in 10 years, we will all be doing this.
Yeah, well, I don't know. I mean, that depends on what you want to do. I mean, if you have a good initialization, I will say this kind of method will be very good. If you start really from scratch, sometimes you have to start from different initialization. While a level set, while a density method, is really more insensitive to the initialization.
People that I know from the very applied point of view that use this technology, for instance, in industry or in physics, they typically launch a lot of calculations starting from very different initial guesses, or they combine this with a pre-treatment by a density-based topology optimization methods. Then at the end, they take the 0.5 isosurface, say, and they relaunch the optimization to have a principled initial guess, for instance.
Yeah, I think that makes a lot of sense. Yeah.
Sure.
Okay. Yeah. Thanks a lot. Thank you, everyone. Just before you go, I will just take over the screen for a second. I just wanted to share Charles's website here because they have the slides at this link up here. They have the slides for all the lectures. So please go take a look at that while you enjoy the YouTube videos again and again to learn everything in depth. So thank you, Grégoire. Thank you, Charles, for
Joyce, thank you very much for
Thank
the
you for
invitation. It was nice. Very nice.
Thank you very much. Yes.
Thank you all for joining, and see you soon.
Bye-bye.